we'll have 3 discussion sessions this morning. The first one is going to be on gas turbine applications. Uh, so we'll get started with today's session. Professor Milind from the University of Cincinnati and Satya Chakravarti from IIT Madras are going to be sort of coordinating or moderating this discussion. Moderating is a very strong word. That means we have very strong opinions to start with, which is a good thing, but I don't know if we do. So we'll just say coordinating. Satya is going to be here momentarily, so we'll get started with Milind. Thank you.
Thanks, Mahesh. First of all, want to thank Mahesh, Sujit, Paul for the opportunity to come here. And I have another conference to attend right after this at IIT Madras, so the timing worked out perfectly well. So for today's talk, since this is a discussion session, what I thought was sort of summarize the 2 presentations that were yesterday by Professor Raghunandan and Mukherjee. They have already gone over certain issues, so I thought sort of remind everybody of those as well as put in some of my input to basically start the discussion. And Professor Chakravarti is here. He's going to take over the experimental part. So we thought since 2 of us are going to do this, I'll cover the modeling part, the issues at least identify those in the first part. Okay. So as Mahesh said, the idea would be to discuss these issues and perhaps identify 3 or 4 topics or themes or that people can sort of come together who have interest in those to take this forward and different types of funding opportunities, perhaps collaborating, writing papers, so on and so forth. That of course is not for this session. I think Mahesh and Sujit will discuss all of that in the afternoon session. But just to keep that in your mind, I put that bullet item here. Okay, so just to remind everyone about gas turbine fuel injectors, atomization in gas turbine applications. Clearly this is a very important topic for the industry because fuel atomizers, this is the first step. You have subsequent fuel mixing with airflow, evaporation, combustion, and all of that plays a role in the emissions that come out, combustion instabilities, efficiencies, and so on. So clearly this is very important. If you want to do a full-scale CFD of the combustor, you need inlet conditions for droplet distribution, both velocity distribution, size distribution, and so on. So atomization is the first thing that you need to have it right before you can really do a full-scale CFD for a gas turbine combustor. Of course, there are challenges, and the first one is that usually these systems operate at fairly high pressures and temperatures. So we need to be cognizant of that, how properties change at that pressure temperature, what we model at lower pressure or room pressure temperature, how does that translate? So those are the issues that we need to look at. Also, in these atomizers, you have swirling flow, which is around the sheet that comes out, or depending on different arrangements, either air blast or hybrid pressure swirl simplex and so on. So that airflow interacts with your liquid flow to cause this atomization. So it's not possible to do the 2 things separately. You really need to look at the aerodynamics along with breakup process and so on to really do atomization modeling in this case. So in terms of an issue, I have identified one here we will come to that at the end to start the discussion, but certainly cold flow modeling, which provides good insights, it provides useful information for design, but we certainly need more in terms of reacting flows, especially with heat release, to really capture the conditions that are present in real scale gas turbine combustors. Now some of this industry does regularly, but not all that data is in public domain. So how do we balance the needs of the industry and for us to look at basic science, which would be in the public domain? So some of those issues need to be considered. Okay, so in terms of modeling, I sort of divided this in three parts. If we are looking at any comprehensive modeling, we have to consider the internal flow of the atomizer, basically start with the inlet conditions, go all the way to a droplet distribution. Okay. So atomizer inlet flow, then we have certain primary, secondary breakup models, and then interacting with the airflow, how does that all lead to, what kind of droplet distribution do we expect at the end. And of course, spray combustion and so on, that also plays a role. So starting with internal flow, looking at, there's certainly opportunity to look at these. Some work has been done in terms of pressure swirl, some in air assist in jet and cross flow type of environments. These are all applicable to real systems and certainly very useful. The flow typically has two-phase interactions, so you need any internal flow modeling requires interface tracking. Usually the flow would be turbulent. So all of that has to be taken into consideration. But I think good amount of effort has been made in this direction to really look at atomizer geometry to how that plays a role in terms of what kind of cone angles we would get, what kind of sheet thicknesses we would get, and so on. And another advantage of this is if you do this with a certain type of atomizers, usually that information will translate very well to applications that are different from gas turbine injectors. For example, I did some work with SC Johnson. This is a consumer product company. They make Windex glass cleaners and mosquito repellent sprays and all consumer applications. And of course, their requirements are very different. They don't really care about spray angles and so on, because when you're spraying Windex, if it doesn't cover the first time, the consumer can spray it again second time. So it's not a big deal for them. But they do care a lot about droplet size. You don't want that stuff to bounce off the glass. It wants you to stick there and then that way clean it. So very different requirements. The pressure differences they work with, in a tiny mosquito repellent bottle are very small compared to what you would see in gas turbine fuel injectors. But again, some of this information could translate easily to develop atomizers that were small scale, operating under small pressure differentials, but would give small droplet sizes and so on. So some of this will also translate to other applications. And again, some issues here. Yesterday, Professor Raghunandan talked about elliptical jets or elliptical geometries. Again, change in geometry, either intentional, such as making it elliptical to make it more unstable, or unintentional, where manufacturing defects or assembly defects can cause certain asymmetries, and then you have to identify those. So looking at both of those and seeing if there are any imperfections that we can really put in intentionally to get better atomization. And Professor Collicutt yesterday mentioned about diesel injectors, how different type of step geometries inside and so on really change the atomization. So even here, some of that can be looked at. So there are certainly opportunities to extend this. Again, a lot of the work that's currently available is low temperature. Going to high temperature, there are issues of interface tracking, whether even if you're not necessarily in supercritical mode, even then property variations at high temperature pressure are very sharp. So how do you handle all of that in interface tracking? That's another issue that needs to be looked at. There are also different types of fuels, especially considering biofuels as an option, as an additive to the current mix. And that would, of course, bring in large property changes. And some of these fuels are, fuels have non-Newtonian behavior. So how do atomizers that are typically designed for Newtonian flow, how would they behave under non-Newtonian conditions? So that's another, and that also translates to rocket fuel injectors, because a lot of hypergolic gel fuels that are being considered for rocket engines now, these are all non-Newtonian fluids. So different kinds of, some of them are viscoelastic. So how does that instability, how does that breakup process, internal flow, all of that changes with non-Newtonian behavior? That's something that can be looked at, and certainly opportunities there, both in gas turbine world and rocket engines. Okay. So if you want to develop a comprehensive model going from internal flow all the way to droplet sizes, here I have a sort of a schematic. This is precious world, but you could change that to an air blast or different type of atomizer. You need to resolve flow inside, and this has been sort of done piecemeal. You resolve the flow inside, use those conditions into a stability or instability model, both linear, nonlinear, to get you some breakup length, certain growth rates, which then can translate into ligaments, which would again then break up into droplets, and you can get a sort of mean size from those. But usually that doesn't give you a droplet distribution. So people have tried different statistical methods, entropy-based methods, to come to droplet distribution. And again, there are a lot of questions in this area. I think in here, perhaps the internal flow is the one that has the least amount of approximations going to using those properties to instability. There are questions of, how do you relate those internal conditions to initial growth rates? Because initial change in initial growth rate will change your prediction of breakup length. It will change your prediction. Once it changes breakup length, it changes the ligament thicknesses, then what kind of droplet sizes you would predict, and so on. So what is the best way to correlate this? That's certainly out open. Perhaps through measurements. We have some measurements that are available in terms of cylindrical jets going very close to the nozzle exit to look at how these waves propagate and increase, and then to look at what is the growth rate of these waves. And but in general, for different kinds of atomizers, I don't think we have that yet. So this one paper, I think, coming out in JFM that has done something, some measurements like this for different frequency of waves, looking at different frequencies for annular sheet. But of course, another problem we have with annular sheet is we can only see it from outside. What happens at the inside interface, it's very difficult to see. So that's certainly an issue. And John Tharakan, myself, we have done modelings of this nature. So this is certainly needs to be addressed. Going from there to droplet distribution, I think there are more questions. This is sort of, at least in my opinion, the weakest link in this modeling efforts. How robust are these? Because sometimes ad hoc constraints are put into these methods to get the right type of distribution. Is it the best way to go? Would assuming a certain type of, say, Rosen-Ramler distribution, and then trying to correlate those parameters to some physical conditions of the sheet, would that be a better approach? I think these are questions open to look at. Okay. Then we have simulations from sort of first principle, and I've given two examples. There are other, Tomar has done work in this area. Then question is of one, computational time. Typically, industries like things that happen overnight, nothing more than that. So whether we have, computational speeds that are now at a level where we can achieve that, that's something probably Marcus can address that later in his talk. Also, a lot of this is primary atomization close to the nozzle exit. So the question is, do we have adequate data in those conditions to really validate all of this? A lot of times we have data which is far downstream. We have droplet sizes, and then there are so many processes that are taking place between just the nozzle exit breakup all the way downstream. So there are questions in terms of whether we need to get that kind of data, and how do we get it. Some of these X-ray methods that are being used in Argonne National Lab now are quite promising, but again, this is something that needs to be looked at. Of course, following that, we have modeling of turbulent spray. Shankar covered that yesterday, and a variety of issues there. When you couple that with combustion, you have reduced order kinetics, how many reactions you need, what type of reactions you need, and finally leading up to emissions and stability. Now these three are perhaps broad enough area by themselves. So I just put them in one slide, but didn't really elaborate on these because each one of this can be a topic by itself to really delve into and discuss. Okay. So what I'll do is I'll give it to Satya, and he can cover the experimental part. At the end, I have one slide where I have taken some of his points and mine and sort of just thrown them on one slide to start the discussion. So we can start the discussion at that point.
Good morning to all of you. Let's just get going with what I had in mind as far as experimental aspects is concerned. Testing issues that I thought were of significance. The basic idea I was essentially thinking is, in IC engines, the idea is they do lots of, they make lots of injectors. Therefore, they want to have a way by which they can quickly test these injectors as they produce them and so on. Whereas in gas turbines, of course, the numbers aren't so large, but typically it's very easy to test these things when you're doing atmospheric pressure tests, but the actual condition, cold flow atmospheric pressure tests, whereas the actual conditions are quite different. So many times it's easy to start with atmospheric pressure cold flow tests, but then there are a number of questions that arise. So it would be nice if we can actually think about some of these issues that have been plaguing us, in fact, for quite some time. But no conclusive answers exist on these things. So what I would like to do is to see if we can come up with some sort of a systematic approach to this. So question essentially is, what's the relative importance of the ambient pressure in which the injection is done versus the injection pressure alone? Then the effect of fuel on air temperatures, and the use of fuel surrogates, the impact of air swirl flow or cross flow aerodynamics on the atomization, simultaneous diagnostics of spray in the surrounding airflow, what data is needed for modeling or validation. In fact, I would like to actually look at the testing aspect in 2 or 3 different ways. One, to produce data for validation of models. Second is to produce data for input to models. And third is to investigate new phenomena that the models can't do anything about. So in that regard, we have to actually look at what is the objectives that we have to carry in our experiments with regard to modeling. And of course, there's another issue about cold. Milind was talking about getting good insights with cold flow sprays, but then you can also take the next step of evaporating sprays or then going all the way to combusting sprays. He mentioned that the realistic conditions are different, so we have to think about these. And then he also mentioned about machining imperfections or small geometric variations. So many times, I'll explain all these things. So in the next upcoming slides, we will just go through. Which one?
Those arrows.
Okay, yeah, sure. So as I mentioned, as far as the ambient pressure is concerned, it's easier to do the atomizer testing at atmospheric ambient pressure. I used the word testing because many times atomizers are just tested. Somebody makes a design and then comes and says, can you tell me what the spray size is? It's as if like we are like a shop. That's typically how it works. But then atomizer design is a completely different story. We will be talking about testing, experiments, diagnostics, these words a bit interchangeably, but they have different connotations. So it's easier to test, as I said, at atmospheric pressure. Then what we find is the atomization is actually sensitive to ambient pressure up to a certain pressure. So maybe relatively elevated pressures, but not necessarily the actual pressures to which you need to go, beyond which the injection pressure is what matters, or the delta P across the injector. So question is, ultimately, how low an ambient pressure can we get away with, because the setup rigs in the experiments can actually be scaled down correspondingly if you are targeting lower pressures. The question is essentially, is it the role of ambient density that is that the ambient pressure causes? A similar question that will arise with respect to temperature. And the other question again is, if we are doing atmospheric pressure tests, are there equivalent atomizer geometries that we have to consider that will give about the same spray performance and so on? So the next issue is temperature, and I'm clubbing these two for want of time. We can condense these slides. When you talk about temperature, there are 2 things. One is the fuel temperature, the other one is the air temperature. So the fuel temperature it influences the fuel properties, viscosity and other properties, whereas the role of ambient temperature could directly influence evaporation rates, as well as fuel temperature would do that as well. But it talked about density effects, which pressure does. Similarly, temperature would do so as well. So question is, what is that effect on the atomization? And similarly, when you're now looking at viscosity and other properties due to temperature, you can also look at matching some of these with surrogate fields, because many times when you're doing these cold flow non-reacting spray diagnostics, we are very, very concerned about safety in the lab. We are much better off actually burning the stuff away because we are very sure that it is consumed. Whereas if it is just going to be causing a mist in the lab, that's not very good. So the disposal of this spray is a big concern. So from that point of view, surrogate fuels would do a lot better. The question then is, what are the similarity rules? Is it just like a Weber number similarity that we have to look at? But what about Stokes numbers, local Stokes numbers versus global Stokes numbers? These are issues that I thought we should think about. Bottom line is, the industry does not like testing anything other than the real thing. This is a big pain, to be very honest. Okay, so we need to get a little bit more smarter about this. That's essentially what I'm saying. So the surrounding airflow is a huge issue actually. So for example, this is the Kaveri engine atomizer. You can see the atomizer in the middle, and then there is a annular swirler. That's a typical arrangement. Now, and we did atmospheric pressure tests in our lab, and without turning on the surrounding co-flow, this is an air blast atomizer, so we got the injection pressures right for the liquid, and we also got the air pressures that is going through the atomizer right. All those things were fine. But we did not turn on the airflow in the swirler around. We simply get the liquid to dribble at atmospheric pressure. Right? So it's simply that the atomizer simply did not work if you did not have the surrounding swirl flow. So similarly, we did this actually experiment for Money when he was at Saint-Gobain. We did this for a spray in cross flow, and then we tried to compare the atomization with and without the cross flow that's obtained with a wind tunnel or a free jet from a tunnel. So the point essentially is, we now try to, the typical attitude or approach, attitude may be a stronger word, sorry. The approach in the industry for quick calculations is, you give me the SMD data, I will just plug it in at the inlet to the combustor, and then I'll track it in a Lagrangian manner. Okay, and then of course the sizes are going to change a little bit. Do you really call that atomization? Right? That may not be necessarily atomization. That is just like redistribution of the droplets. So there is a significant amount of secondary atomization that goes on because of the surrounding airflow, which probably is not taken into account in most modeling aspects in a Eulerian Lagrangian framework. The most important thing in my mind as far as diagnostics is concerned, moving away from testing, is what do we do to actually look at the airflow that's around the spray, particle for particle. That means you're looking at spray particles, the droplet particles. Surrounding it, there is an airflow. Can we actually track both? So measuring spray particle and airflow velocities at a location is required. It's a very interesting thing, because you can actually get phase interface shear, which is pretty interesting for interface tracking, model validation under turbulent conditions. And question is, what about the methods? Okay, how do you really do this? One possibility is we say, okay, spray actually scatters a lot by me-scattering, so the me-scattering intensity is very high, whereas if you now preferentially seed with much smaller particles, narrow cut distribution for the air, you can threshold, but there are big issues about that. Then is it possible for us to actually look at like a simultaneous pliff and me, and then use the pliff for the spray velocity versus me? So again, there are issues around associated with this. So this I thought was a very interesting or very important thing to do. So the other issue that I raised was, what exactly are we looking for from experiments with regard to models, right? So the most popular thing to do is PDPA. So PDPA is like a behemoth. You just get this, and then you say, oh, I got PDPA, and then you start doing things. But you get data that's reliable only slightly away from the nozzle, but pretty much that's history. I mean, everything has happened there. We are really looking at the after effect, strictly speaking, right? So what about data closer to the nozzle? How do you actually approach this problem? And it's not as if like nobody has thought about these things. Things are going on, but we have to firm up, the ideas about these things. So For example, is it possible for us to actually statistically quantify ligament shapes? Okay, I'm talking about shapes, not just sizes. All right. This is because there is a person who comes and does modeling, and then he shows up all these nice ligaments like what Milind was showing, and then he finally tests PDPA data further downstream and say, yes, I got it right. Okay, you could get the same PDPA data with a different ligament breakup model. That is not in reality. So there must be a way by which we actually statistically quantify this experimentally so that we can pin down the modeler and say your ligament breakup model was wrong, although you got your PDPA data to match, right? And of course, as I said, this is also pretty important because you're modeling, you can get a lot more data for aiding the model. It's not about actually pinning down the modeler and say you're wrong, it's about helping him, right? So can we actually get more data on interface shear and turbulence quantities and so on? Good. So what about cold flow testing? As I said, just like atmospheric pressure testing, cold flow testing is pretty easier, and many times it is claimed as enough. You just do this and you can just get going with your activity. But what happens in reality is in gas turbine combustors, and keep in mind this morning is about gas turbines. It's not just about any spray, right? Gas turbines have complicated geometry, right? So when you have complicated geometry, you now start thinking about putting this in a complicated geometry with optical access to actually look at what happens. You get the windows to be fogged because you're in a confined environment. You're better off actually working with an evaporating spray, which evaporates by the time it gets to the walls. Therefore, it doesn't really fog the walls, and you have good access, and you can do better measurements, which is actually closer to reality. All right. So, are we better off actually dealing with evaporating sprays right away instead of cold flow? In that case, what about the volatility, right? We now have to come up with a surrogate fuel which is a bit more volatile than the actual fuel and so on, so you get into problems there. Combusting sprays, as Milind pointed out, we have density variations due to temperature that alters the flow field and therefore the spray field and so on. So that of course is a reality which we would like to test, but what about understanding? We can't do the real thing completely. Finally, the last part, atomizers are designed with very, very close tolerances. It's a very, very interesting trade. What happens is there are small manufacturing defects that will cause huge asymmetries. 10 years ago in IIT Madras, we had a seminar, and the late Jerry Faith came here, and then he made this statement that just is in my mind all the time. He said, he probably learned it somewhere else. He said the atomizer is the kingpin of the combustor. So basically what it means is like you now slightly turn the atomizer this way or that way, you can get rid of a hot spot here, or get NOx to come down and so on. So this is like you have a very fine control in a way that we don't understand, okay, with the atomizer, and small imperfections can actually cause huge asymmetries. The question is it possible for us to quantify this a priori, this sensitivity? Okay, so there must be testing as well as some sort of anticipated CFD that needs to be done in a systematic manner to anticipate the sensitivity, right? And then we also know, for example, that atomizers are actually mounted within the swirlers with allowance for axial and transverse misalignments. You know, when you're mounting these things, we go through these things in our lab all the time. So when you're mounting the swirler and then the atomizer, they are not really fastened together in any manner. You just insert the atomizer there and then let it be there. So you could actually have the swirler here and then the atomizer this way, that way, axially, or a little bit off center as well. So the question is, what about these effects on the design performance, right? So are we really quantifying these things? So I think that's Milind's slide. You want to go?
No, I mean, I just sort of discuss this, but put something together. The new part is just last two bullets.
Oh, there it is.
Keep that because you'll need it. So last two bullets. One is looking at the CFD community went through a benchmarking exercise. You know, people working in different with different models were given one data set to validate and look at. So whether something like that would be worthwhile doing, taking a atomizer that would be in public domain, you know, look at some detailed measurements and have those available for fault model validation, all as model input. And something that Jeff had mentioned yesterday about sort of a network in IC community. So something like that, whether it would make sense. I know that the Indo-US forum has some funding for developing networks, and so perhaps that could be a way to galvanize people to come together and look at these issues. So that was what I added at the end. So now we can open this up for discussion. Any type of comment, issues. What I can do is I will take a marker and.
We have a couple of students taking
Oh,
notes.
taking notes. Okay. So,
And, but you can also
scribble if I like. Okay. So anybody has about experiments,
and also
anything
this
else?
this event is on videotape. We'll make a DVD of it and mail it to everybody. That will also be available, all the talks and the discussion.
Correct.
No, what your case on surrogate fuel, what is the fuel you are planning or tested with
Actually,
other?
Satya, you might want to keep your mic. Yeah.
no, this discussion that I'm throwing up is not exactly based on what we have done. We have done water, and now people are saying do Jet A directly. Okay, so don't even think about surrogate fuels. But there were some companies that came to us and said you use surrogate fuels because they're also worried about safety, and just as we are. So there are issues there.
I have to understand it's very difficult to simulate gas turbine condition to test air blast atomizer precision. But there are facilities available in UK, Jesuja, you might have heard. He has developed such a facility where
No, the point is it's possible to do so. It's not impossible. Question is, every lab, if it has to do that, that's going to be very, very expensive. Whereas you want to be able to go to the university next door and get something done. We don't want to really demand that you actually build an engine and then do this.
no, you should go as close to the design intent.
That's obvious.
It will not be possible to simulate exactly the gas turbine condition. Go for higher and higher so that we'll get a better insight into.
I know Professor Neighbor talked about surrogate fuels in IC engines yesterday. So are there similar challenges? I mean, the challenges obviously are similar, finding a surrogate. Can you sort of expand on that, please, and see what are the challenges in coming up with a surrogate? I mean, what are the issues to look at?
Well, I think we borrowed significantly from some work in the Air Force community, specifically the work going on at Princeton, and their work in looking at surrogates for Jet A fuels, right? But most of that work, again, is focused more on combustion kinetics rather than atomization and spray formation. So somehow I think we needed to connect those two together, and really that was the motivation for us, is to look at, okay, we want to understand from a basic principle and provide data that modelers can use. Obviously it's difficult to model complex fuels like Jet A or diesel fuel, so if we can come up with a surrogate that is easier from a perspective to model, but then what are the characteristics of that surrogate it needs to have representative conditions in the nozzle that may include cavitation and primary atomization and vaporization. I don't know that we know the answer, because at some point we too would like to say, okay, we can do this surrogates work on a very small scale, but at some point we need to show also that those surrogates really match the combustor performance, so in an engine. And so if we come up with surrogates that are really expensive, we can never get to that point. That doesn't need to be done a lot, but someone along the way, I think, needs to say, okay, we tested these fuels, these surrogate fuels with Jet A, or in our case, ultra low sulfur diesel or whatever, and the emissions matched or whatever characteristics. So I don't think we know, but I think, my discussion was, okay, there's been a lot of work, less work at looking at what the surrogate requirements are from the atomization and spray characteristics.
what we need is basically transport and thermodynamic properties, and we know them for pure substances. But how do we actually, come up with what it should be for mixtures? As of today, to the best of my knowledge, we continue to use, what Reed, Sherwood, and others have published in terms of mixture laws. And there is deviation from non-ideality for a lot of these substances, particularly when you, say, for example, represent Jet A by an alkane and an aromatic. The deviation from non-ideality for the aromatic would be really fast. So how do you actually bring in mixture laws? These become practical problems for the modelers to actually represent, say, enthalpy of vaporization. You want to actually bring that in. And how does that change with pressure, which is kind of very important for us to know, or surface tension.
Yeah, I'd say this is really a shared activity, right? It's not isolated to gas turbines or engines. It's really something that we could work on together.
Yeah, because from kinetics, we can actually come up with a real fancy representation of a surrogate, which includes, a bunch of aromatics, bunch of cyclohexanes and hexenes, and, alkanes. But do we have properties for all of them? You can look up to NIST data. Some of them you may not have.
Yeah, we don't.
I think it's very difficult to have a surrogate for cavitation, for instance. So is it possible to find a surrogate both for cavitation and for combustion?
Probably not. I don't mean to be rude. I just honestly don't think, I mean, you've got so many different characteristics and parameters you're trying to match and properties that, comes down to working with the real thing is, but even diesel fuels vary from season to season, right? So there really is, in many cases, not one definition of what the real thing is.
I would like to talk something on that MEF, maximum entropy formalism for droplet size distribution. Achinto actually talked about it during his presentation yesterday. We recently tried to develop a comprehensive model using breakup theory and followed by maximum entropy formalism. Now, it is a statistical method, and as you all know, that to get the droplet size and velocity distributions, we have to go for some statistical method or other. Now, it has been seen in the literature that MEF is one of the mostly used statistical method in order to get the droplet size and velocity distribution. Now, what we did, actually for those who are not so aware about the MEF method, what it does is it actually maximizes a term called entropy or information entropy, which is related to the distribution of the droplet size as well as velocity. And it does that maximization under certain validating certain constraint conditions. Now, what we did in applying this MEF method, we use the conservation equations as the constraint equations, conservation of mass, momentum, and energy between the sheet between the liquid as it comes out of the atomizer and the final droplets. Now, here what we have got or what we have seen in the literature and during the review process of our paper, that there is a lot of uncertainties in the conservation of energy equation. What we did, we actually balanced the kinetic and surface energy in the liquid as well as the final droplets. But the question comes whether the internal energy, Achinto actually also pointed out this, whether there is some conversion of initial kinetic energy to internal energy in the final droplets. Actually, this is given in the paper of Mehring and Serignano. They showed that there may be some change in temperature of the droplets after the final atomization as a result of this increase in internal energy. Now, there is not much confirmed literature on it, maybe some experiments can be performed in order to see about this so that it can be incorporated in the model as well. Also, what we found is that there is not much data regarding the velocity distribution of the droplets. Some data are of course available regarding the size distributions, but velocity distributions data are not available in the literature. So it is very difficult there to match the validation with the, particularly on velocity distribution from the model and the literature. So these are some things what we found during this work, and some experiments or something can be carried out to go further on this line. Thank you.
Hello. Yeah, this is Dalton Moore from GTRE Bangalore. Yeah, from yesterday, all the presentation, whatever I have seen, that it appears that all the works are related to modeling and simulation only. So my doubt was that whether experimental work are going on or not. But Chakravarti sir has told that I was happy that some work is going on that area also. But I am surprised that we are not talking about what are the standards are being followed for characterizing these atomizers. Like SAE standards are there, but nobody is talking about that. What are the practices are following for characterizing? Because finally everything is related to SMD, cone angles. Somebody will say distribution, and somebody will say that velocity distribution. But nobody is talking about that. Okay, and as an industry, we think that everything has to be done as is condition as a gas turbine engine operates. But when that is not possible, at least standards has to be evolved that what practices should be followed by engine houses. So that we are not talking about anything related to that. And suppose that those things are not available as a, then quality control, how to be controlled, and what parameter we should look before fitting in the engines. Like those things also to be addressed somewhere. I don't know how to raise those issues. So these are my opinion on these atomizer things.
Can I let you be? Okay. Can I? I think I just want to respond to two things that you raised, Dalton. Uh, I think I'm a little unique in that I'm the only one that has actually made spray nozzles in the industry. I worked for about 5 years making them. It's very difficult to agree upon the simplest of terminology like spray angle. Okay. We had 5 nozzle manufacturers at a table like this. It was under the auspices of ASTM, which is the standards setter, so to say. And we went through a long discussion to agree upon spray angle. And it has been codified. There is an E standard. It's called E.34. ASTM E.34, if I remember that right. I may have the 34 number wrong, but it's E dot some number that has all the spray terminology standardized. And so you can always say, I tested this nozzle under this by this standard test procedure, and this is the angle that I obtained. Yes, that is available. How widely is it followed? Because ASTM standards are entirely voluntarily followed, unlike SAE standards. So it's up to the user to request that it be adhered to. Okay, that's the first thing. Second thing, I think there is, as far as spray nozzles go, like Satya alluded to, there's a lot of variability that comes in the manufacturing stage. And all of that is masked by the end result. So to say, if I can hit 2 or 3 end result parameters, there may be variability in the nozzle geometry, but I feel like I've accounted for all of those variations. In other words, I've cancelled out the variations, and the net result is that this nozzle A is the same as the one I made yesterday. Okay, so that is the general approach that all spray nozzle manufacturers take. So you don't require geometric tolerancing, you require performance tolerancing. It's a very different approach to making products. And it's there because it's a very complex piece to hit geometric tolerancing. So I think from that perspective, we should let these guys have a longer leash and live with what they're producing. They've done it for a very long while, very cheap. One of these aircraft engine nozzles sells for a few $100s. It's completely unfair to the manufacturer, but they've done it well. And to think of this as the kingpin and to think of what the engine sells for, it's very unfair. Okay, so I think they've done we should try and see how to better help them and to sort of go towards this geometric tolerancing if we can. What that requires is a model that relates performance to geometry. I think that's one many people have talked about it, and we need to discuss that as well. Thank you.
That what I feel that this standard should be there, however it will be voluntary, but it is also required for the education sake. And it is not that we will leave the, like the kind of thing or control the manufacturer. No. Manufacturers will do their own way, of course, depending on the client's demand. But however, as an academic community, they should look at those aspects for the future benefits, for the more development kind of thing.
Staying with that, let me also give you a perspective. The manufacturing may not be as, as difficult or as critical as stack-up is. When we actually put the nozzle together with the swirler, is where we have deviations. And that is something which is not going to be reproducible in a lab. It's going to be very tough for someone to actually reproduce the way we have actually put the nozzle and what's the immersion and what is the sort of misalignment. It's a stack-up thing which is going to be different. Remember, the swirlers that sit around the nozzle are not manufactured to the same level of tolerance as the nozzles themselves are. Okay, so there are practical issues in actually trying to so-called match up and get the zero sum of your total stack-up.
Are there any sensitivity studies on those?
Yes, we do a lot of the sensitivity studies for the stack-up. We also do sensitivity studies for the swirler and the nozzle together with immersion and so forth. So we have information of how the nozzle will behave.
That brings me to this point, which whenever I see both modeling in gas turbines or IC engines and industry uses codes, and the one thing that industry could give the academic community is that sensitivity, because then you would put your efforts in modeling those most sensitive parts rather than running after one particular detail, which is what typically we end up doing. And nowadays, this uncertainty quantification is a big deal. It's a well-established procedure by which you can propagate uncertainty in the inputs and the model constants through your code, which should run overnight, right? Because industry won't touch a code that doesn't run overnight. So then it should be relatively easy for the industry people in this community to tell us what are the most uncertain things, what are the things that are most sensitive, that your prediction is most sensitive to, and then people can work on that.
Yeah, staying with that,
Right.
what we would normally get is what we call as qualitative assessment of sensitivity. So in that sense, it's not going to be a number-to-number comparison. We kind of term it as directional accuracy. So I know nozzle A and nozzle B behave in a particular way. So I would know what's the sensitivity with respect to A and B in relation to a particular parameter or an expectation. It could be combustion efficiency, it could be pattern factor, and so on. So a gross CTQ is kind of matched up to understand what's the sensitivity. And that's most important for us. And I think some of that information we normally publish in conferences. The more recent nozzles we don't, but I think for example, for the CFM, we have published that information. I think there's a lot of that information available.
I'm talking about a broader thing, which is in the discussion, people are talking about surrogates. How important is it to match the surrogate? How important is it to match the nozzle geometry alignment? The question is, which is the most important thing to the end result? If we know that, then people would work on that preferentially rather than spending the resources on,
Can I still take time? Yeah, go ahead. Okay, I had a couple of comments from the industry point of view. Let me kind of, based on what Milind and Satya's told us. First is getting inlet conditions right. I think you guys kind of captured it well. The more important thing for us is the near nozzle flow. And I think it's fairly trivial for a lot of people to assume that there is atomization or primary atomization that's happening at only one location. Unfortunately, in a real nozzle, we have impingement. You have venturies and you have impingement, so we have multiple points from where you will have atomization. This is something we've not got really well. We don't know where impingement happens. It's absolutely important for us, and the reason for that is we have issues with heat transfer. The nozzles get really hot, the nozzles go. So we need to know where impingement happens. And I think, experimental techniques as of today, to the best of my understanding, don't seem to give us that information. We just do not get enough information right into the nozzle.
I think we simply haven't tried.
Okay, okay, so I'll take that point. I think that is something that the community, the research community needs to take as an item as to how we can advance experimental methods which give us information right at the origin of spray and at impingement. The bigger problems that we have are obviously combustion efficiency. So how do you qualify or quantify impingement breakup to efficiency is something that needs to be studied. So you can't do cold sprays. You have to do reacting sprays. And you need to give us that kind of information. And I think Satya referred, when you started said you put the swirler and therefore and then you found the spray it to be different. Yeah, that is the way it should be. What we don't understand today is the relative, you could say, orientations or rotations of the liquid fuel sheet in relation to the air circuit. We know it has a bearing on acoustics. We know that there are certain scenarios where co-flowing streams have better acoustic stability. Now, why? What is the reason? We don't know. But we've used that as a rule of thumb to design lean systems. This is something that the community needs to investigate. What is the relationship? And let me also caution you that the air streams that we use need not necessarily be single swirled air streams. There could be multiply swirled air streams, and the fuel streams could also be swirled. What is the relationship? So there is a reasonable amount of complexity in actually understanding this. But we know it has a very strong bearing on acoustics. We know that if we get this right, we can design lean premix systems which are fairly stable and can go to low equivalence ratios. Today, we are not in a position to have those qualitative rules. And I think that is something that the academics should seriously think about.
What's coming off from what you said about the sensitivity of the stack up of atomizer and the swirler, as well as what you just mentioned about the role of the orientation on the acoustics and so on, is you seem to have a qualitative approach about this. The question is it possible for us to quantify it in some way? So in which case we want to actually systematize the investigation.
That's right. And as of today, the industry does the design based on what worked well for them. So we necessarily do not expand our design space dramatically. We can't do that. Okay. So we always make an incremental, invention. We don't actually go to a radical, design. But the industry, but the academics can actually look at very different configurations and tell us, what should be the direction that we should be taking 20 years down the line. If you look at emission regulations insofar as aviation is concerned, today what are applied are called Cape 6 limits. The long-term technology goals for us is by 2026 we'll drop this down by 75%. And for us to do that, we think we should go lean premixed. But for us to go lean premixed, we have all these challenges. And emissions are important. NOx emissions are important from a high power point of view. But how do I operate the engine at low power and at sub-idle when the drop sizes are pretty large? How do I ensure that I have reasonably high combustion efficiency while doing this is our biggest challenge. So I think these are things that you can, this is the industry perspective. So these are problems that you can look at and see, how fundamental experiments can give us insights, and we can leverage that to help us do better designs.
The other problem that I have with your mentioning combustion efficiency as like the global marker of or the final output is what Mahesh was saying. You could have 10 different configurations giving you the same combustion efficiency, and you're very happy with all of them, without understanding how you got from where you were to what you got. So question is, do we think about like metrics to look for that are closer to the atomization process than the final end result of combustion efficiency?
Well, we have some, and if you get us an experiment and tell us, I'll tell you whether this is good enough or not.
I I just want to talk about rockets in a slightly different sense, but Tharagan is here, maybe has some idea. There's this offset between the fuel and oxidizer. They critically play with it to improve the C-star efficiencies dramatically. So maybe there's something to learn from them. Maybe.
And we have tested many injectors, mainly cold flow, and of the same design, that is the same dimensions and same tolerance level. But we have seen a lot of variations between the hardware to hardware in terms of its spray angle, spray uniformity, and droplet size distribution. We find that there are, during manufacturing, there are deviations caused due to the machining aspects like burr sitting and some location of the flow passage. And also, if you have a coaxial injector, swirl injector, manufacturer, if there is a deviation, a small, if there is a deviation in the concentricity, it can lead to a large change in the flow spray pattern of the propellant that is flowing through the annular flow passage. That can lead to large change in the combustion efficiency. And also that reflects in the spray uniformity. And corresponding changes, if I put for a single element thruster, the variation in C star is about 2 to 3% change we have observed from a good injector to a bad injector. And also the one another problem what we have noted is the drilling of the holes, that is the cylindrical holes, that is for the impinging jet injector and all. If there is a spray misimpingement is possible if the holes are not drilled properly. And also there is a hydraulic flip phenomena we have observed in certain orifices of low L by D ratios. That can also lead to changes in the injector performance. And also we have observed certain the burn throughs in certain cases because of the injector associated, that is the deviation in the injector characteristics.
I would like to comment on this sensitivity analysis. From my point of view, from the industrial side, when we design injector, of course, we can make thousands of computations and we can also make thousands of physical analysis. But there is also another way to make this analysis is to use some data mining. That means what is most important in our industrial application is to have data of everything. That means even if we have data that are not relevant, sometimes we can find the physics. So from my experience, we have noticed some physical phenomena in our injectors when I was previously in Sango. The physics through the acquisition of the data during 1 year, you have thousands or millions of data, and then you have some mathematical techniques that are able to say which is the leading parameter. That means, and we found out with an injector, even without measuring anything, that in some injectors, the pressure was important. That means in every plant, they regulate the pressure. They put 1 bar, 1 bar, and then they have also flow rates somewhere. And using all this data, thousands of data, that means it's many gigabytes and gigabytes. So if the people from that do mathematical analysis, they are able to derive what is the main parameter, what is influencing. They can show you that this parameter is not playing. And if you make the PDPA analysis, you can find the same results. So data mining, from my sense, is very important. That means behind data mining, that means we should make an acquisition of the maximum data we have every day. And we also found that in one plant, there was a fluctuation of drop size, but in fact, it was that we produced matte, and in some conditions, at the end, the product was more wet than the other one. And using the data mining, we found that there was no problem with the injectors and the regulation system and so on. It was just because there are fluctuations by day and night due to the moisture rate. So now, at the end, every plant is regulating the flow rate from in the morning and in the evening. So just to show you some examples. So it's very important for me, for the sensitivity analysis, just to acquire the data. That means to have more diagnostics, more measurement, let's say, from an industrial point of view also, not only in labs. So.
Yeah, actually, continuing from what Mani said, I mean, again borrowing from a quite a different field. I mean, this there has been in process industries, particularly like in steel industries, there has been a lot of effort in developing so-called hybrid models kind of thing, which kind of balances the experience gained from experiments like data mining and those kind of techniques, and whatever little physics we know, clubbing them together to get kind of hybrid models which where we do some amount of modeling and then do some amount of experiment and using some data mining to correct the models and in a way go on an adaptive kind of modeling. With those inputs improve the model, and then again maybe that kind of approach I'm not sure whether it's being followed in the industry in the combustion community, but I've seen that thing very regularly done in, for example, in steel industries.
To add that there is now, everybody knows about the high throughput method, so it's a big words, but of course we can use it. That means in continuous conditions you can make a variation of the pressure so feeding an injector of the flow rate and so on. You can make acquisition of the data, and then I'm not competent enough, but there are some mathematical people from mathematics, engineering and so on that are able to, using these high throughput results, to determine exactly what is the parameter which is influencing. So that means a continuous analysis of something in a short time, and so we can apply data mining, let's say, data mining and high throughputs to study sprays and injectors. So.
I have a couple of comments here. Okay. There's another area that I think we've not yet settled really well, and that is with respect to transcritical and supercritical flows. I think there isn't consensus on what is called as supercritical and what is called transcritical within the community. This is an area that is of absolute interest for gas turbine combustors because we're going for high OPR, and we would like to understand and know how we can either get enough information through experiments or how we can model transcritical and supercritical fluid flow. And likewise, there's been a lot of information for coaxial jets, but very little information on jet and cross flow. It started recently, but I think experimental information on jet and cross flow in scenarios where there is pressure gradient, there is swirl, is very little, and we have no basis or benchmarks to make comparisons for exercising any of the established models. We don't understand the influence of jet blockage as well. Presented in combustion symposium, the level set method. We're looking forward to using it at some time. But I think we really need a lot of help, particularly in jet and cross flow, in supercritical fluids, and in transcritical fluids. Measurements are very scanty. There's just one or two groups that are doing some measurements now, but I think that's something the community should focus on. It'll help us, develop really lean premix systems at high OPR. So that's our selfish interest.
I would also like to know one thing. We have seen a lot of work on biofuels in IC engines, but what is the status of biofuel application in gas turbines, particularly in aviation sector, for example? If anybody can throw some light on it.
You see, insofar as aviation is concerned, there is an ASTM spec for Jet A. So long as you meet the ASTM spec for Jet A, it's our contention that it's not going to be really difficult to burn that fuel. And we've demonstrated that in a couple of engines, and with about 15 to 17% biofuel with Jet A, and we have found no problems. The ASTM spec for Jet A is pretty rigid, so long as you meet the spec, I think it should be okay. The process of actually getting that, the Fischer-Tropsch process and so on, getting that fuel, I think is not so much that the aviation industry or the engine manufacturers are really bothered about. I think that will be someone like Shell and others would do it.
So earlier there was a little bit discussion about X-ray data from argon. It's a question for modelers. I'm a modeler myself, and I do use the X-ray data for IC engine applications. My question to the modelers in the aerospace community, have you guys tried to use the X-ray data? And if not, what would you like to see from the X-ray data so that you can use it for model development and validation? And this is my selfish interest because I come from argon, so this is of my selfish interest, but if you can shed some light on that, that'll be really useful.
Hello. Yeah, I don't think it has been used much yet, but this is something very promising that was discussed, I think, in last ILAS conference. So you'll probably see more proposals and applications for that. So it's something very promising method to look at.
Thing it doesn't do is give you a droplet size. It just gives you a distribution, mass distribution, and it's near nozzle. But it doesn't give you anything about the atomization characteristic. So that's something to keep in mind. It will give you what is the dispersion, it will give you what's the spray penetration, things like that, but it will never give you a droplet size. Maybe phase contrast technique has some potential, but regular X-ray radiography would not actually give you a droplet size near nozzle. So that's something to keep in mind.
See, that's the point I was making. Near nozzle, the droplet size is not well defined, the first place. So, whereas it's quite well defined a little farther away. So, what we really need to do is do I wouldn't say simultaneous measurements, but you should do measurements of both kinds. That means you do the kind of diagnostics you're talking about near the nozzle, but also step off a little bit further away with the same diagnostic techniques to start looking at tandem measurements of droplet size to correlate. And then we have to actually extract some statistical feature out of this that can be penetrated upstream to quantify what's going on there relative to droplet sizes.
Something else that we are actually considering in the IC engine community is actually to take information that you can get from this X-ray data, avoid the near nozzle, but get the data from the X-ray studies a little bit further downstream, where you can actually use the Lagrangian kind of approach. In the near nozzle, using the Lagrangian approach is kind of iffy. So take data from the X-ray and initialize your simulation a little bit further downstream instead of trying it at the nozzle exit. And we have been discussing this. We have never really started doing this, but this is something that we are considering, and that might be something of interest to the industry also.
Just going back to one of the points you made, I think looking at different swirl configurations relative to liquid and so on, this is something very interesting. But again, as Satya pointed out, going all the way to combustion efficiency, especially from modeling point of view, is often very difficult because the person who does multi-phase need not be the person who does all the chemical kinetics. So perhaps, putting these problems into some smaller
sub problems. Maybe that's something we should look at to.
I was referring to that with respect to acoustics. And my thought is you can look at configurations and actually do simultaneous velocity measurements and look at the recirculation zone. Okay, uh, there are correlations. I mean, not mathematical form, but the way the recirculation would behave versus what you can see as signature for stability and instability. And you can actually classify nozzles. So these are things that the way we look at it is we actually do a simulation, look at the flow field, and we make assessment of flow field and we verify it against an actual engine test. In the engine test, there is no flow field measurement. There's only a Q light. I mean, basically, I look at a response. And that's how there is weak correlation. So if you ask the engine manufacturers, there really isn't data for us to give you to get insight. We have hypotheses. But what I want the industry, what I want the academic community to help us is either prove or disprove or give us directions on this hypothesis. And I think we should make some start in this direction. That's what is my opinion.
I don't know about acoustics, but we faced also on some problems in some industrial applications of sprays due not to the spray. Yes, it was due to the spray on the modeling side, but it's because also we don't take into account the modeling of turbulence is not sophisticated enough. So how far are dependent all these results on the prediction of turbulence of the gaseous phase, first without any droplet, and then when you have the presence of the droplet, how far is there a modulation of the turbulent phase of the carrier, the turbulence of the carrier phase due to the presence of the droplets, and it's dependent on the size of this droplet and so on. And sometimes you can have some differential diffusion. So physically, you can have some ignition somewhere, and you cannot have ignition in combustion problems. In other problems, you can have some evaporation rate, which is not, when you model it at least, which is not very consistent with what you observe, and so on. So I think from a modeling point of view, still the turbulence models need many developments for thousands of years, I mean, but we need also to model, so nobody is modeling this influence of the droplets on the carrier phase. So I haven't seen, so there are some models, but if you put them, it modulates too far, so most of the people, they just switch it off. So.
I think staying with turbulence modeling, I think I had a discussion offline with Professor Shankar, and we were talking in the context of LES, how do we actually develop subgrid models for two-phase flow? I think that is kind of a challenge. Today we don't have anything really good. How do we actually build that up is something that the academics can actually look at. Because LES we are going to use, we have started using, we could say we are using it reasonably extensively for a lot of our work. So 3 to 5 years is going to become the bread and butter for the industry. And unless we are geared up today to actually implement some of the models that will help us solve two-phase flow problems, we would probably be stuck.
As far as I'm concerned, it's one of the problems I am looking at, the influence of turbulence on the spray formation, not the modulation of turbulence by the droplets, not yet, but I think it's one of the key points, and it should be answered whether or not turbulence has an impact on the spray PDF, for instance, or I think yes, but if you don't go fast enough, and most of the time academic don't go fast enough because it's more difficult, you can see the effect of turbulence.
So since we are talking about turbulence modeling and LES, a natural question for me is, do you actually see some advantage in terms of qualitative and quantitative predictions when you use LES, higher resolution LES versus a lower resolution RANS? In IC engine modeling, when we use RANS, we can actually get most of the global characteristics very well. Uh, for example, flame lift-off length, we can get fairly well using RANs. Ignition delays, we can predict fairly well using RANs. So the question really is, when we are using LES, what is that we want to validate against? Is there any advantage of using LES over RANs?
Since it's a more broader question, not necessarily confined to sprays, let me answer it this way. And most of the combustors, the combustors which have dilution holes, and there is what we call a scalar mixing, uh, you will generally not get good agreement with RANs on pattern factor. Okay, you will get a fairly good agreement with LES, and this has been observed in spite of the fact that we may not necessarily resolve the boundary layer in the wall and so on. The core mixing that happens, any scalar mixing, okay, you get much better results with LES. And particularly the guys who've been using a lot of the industry, power generation work where they use gaseous fuel. Okay, you cannot get gaseous fuel air mixing with RANs. This is the conclusion from the industry. A lot of people who may disagree, but we are damn sure that you can't get it.
I'd like to add to that. If you look at Dan Howard's work, um, he's shown very convincingly that the cycle-to-cycle variation you see in IC engines cannot be captured by RANs, but you can get it with it. So metrics may be different. Right. So there are structures, definitely from the viewpoint of structures, I think that's the way.
That we have a better prediction of the mixing with the LES, but concerning most of the the combustion models, they have been developed in the RANS approach. That means you fuse then a simplified thickened flame model and so on to close the combustion. How far are you more precise than the good RANs? That means most of the people that are doing RANs, they use the K epsilon. So on. Since the K epsilon, we have made major improvements. That means we are able to model correctly the micromixing. So you can use the SSG model for, let's say, for the Sargar model. And using this, so from my point of view, in my experience, industrial experience from now, during, so it was in rocket engines and also at Saint-Gobain and so on. So I have not seen so many adventures. Of course, in terms of mixings, if there is a problem of pure mixing, LES is as an advantage. But in combustion, speaking of combustions, you should not forget that the combustion model afterwards has been built completely using most of the formalism of runs. So the shear, the stretching, and so on, whatever. So today there is no combustion model built with LES thinking. That does not exist.
With your permission, I just want to ask a question to mostly the academics, and then maybe the industry people can also chip in. We don't have any physics majors here, so I'll go on a limb and say this. I'll take the approach that Professor Abraham suggested. And where is the gas turbine efficiencies have plateaued off for the last 20 years or so. Now, where is the biggest bang for the buck against this plateau? Okay, I think that is a question that we should ask ourselves as engineers. All of us here are engineers. We want to do sound science. All of us want to do that, but we cannot lose sight of the real goal, which is taxpayer money being used to return back to the taxpayer something. Where is scope for improvements in combustion efficiency, gas turbine performance efficiency? I just want to hear the room's view on it.
I came late, so I was not talking. I got a feeling that academics ought to know a lot more about the intricacies of the process, the physics, everything. I think the onus is on us to have the complete understanding. The industry may not really quite, their standardization, as somebody was pointing out, may not really look at all of them. I think they need not even look at all of the details. That's if I'm an aircraft engineer, I don't bother about what happens inside the engine. I want the engine performance finally. As a combustor engineer, I think Now, they might look at overall performance in terms of their pattern factor or something. I think the atomization group as such has to look at all details in some sense. I think it's our understanding eventually. I think it matters a great deal. So questions that were asked, such as near nozzle flows, it is a problem. All of us know that we're all happy measuring all parameters downstream at some distance and then say we simulate beyond that and so on. But that's fine as far as you want to make combustion performance, but then it's not sufficient for our understanding. I think that's where I think we should look at what diagnostics we need to develop for such final details. I think there are questions like trying to say combine different types of diagnostics together. I just had a comment. I was wondering whether we should look at some sort of an inverse modeling, which I'm not very clear. I'm just throwing the idea that you have a near nozzle characterization of certain parameters. You may not be able to measure drop sizes at too dense a point. The sheets may not have been broken completely. But a little downstream, you have complete characterization of the drop size distribution, the velocities you can measure today. So at the near nozzle conditions, maybe you may be able to get the sheet thickness, maybe the mass distribution. I think an inverse problem of that nature may be performed. I think that may be more useful for our immediate understanding.
Well, a couple of comments. First, on the near nozzle measurements, sheet thickness is probably a local quantity, but mass distribution is like a global quantity. So there must be some sort of a statistical quantity that comes up that characterizes it much more locally than these couple of parameters. So I think we should search for that. Like, for example, ligament shapes and so on. That's what I was mentioning. The other question, the other response to Mahesh's rather fantastic question is what's happened in the last 20 years to deflect off from what you're saying. I mean, it's been a case of shifting goalposts. Okay, combustion efficiency is really nice, but we then shift our attention to emissions and stability, and then now climate change and so on. So at some stage we are like, okay, fine, just live with whatever combustion efficiency we get, and then let's do the other things that are more pressing and more immediate. And those things are pretty challenging as well. Right. If I can take this opportunity, I would also like to ask this question to the community. If the industry really wants us to do only the real thing, doing atmospheric pressure tests or cold flow tests or high pressure spray rigs, high pressure, high temperature spray rigs, combustor rigs, all these different levels of testing, are they all like toys until we get to the real thing, or is there still some sense in doing these things? Would people get some, or let me put it more positively. What do we get out of each of those lower levels of testing that we can take home with for the benefit of, let's say, modeling or whatever? Or should we always target the full thing finally?
See, Satya, it depends on what is the insight you're going to offer with low-level testing. I mean, if it is the same level of detail that is going to come out from a low-level testing versus what you can do with a more sophisticated high-pressure testing, then maybe it's not worth it. Okay, if you are really constrained from actually, say, optical access, from measurement and so on, and you think that there needs to be really simple tests that need to be performed which can give us that information, yes, I think that's good. But you also need to tell us how is it going to correlate with what is going to happen high pressure tests or a more realistic test, and what have we learned from this simple test that we can actually now make the more complicated tests possible and feasible. I think that is the thought process that needs to be a part of the academia. While the fundamental simple tests do give you a lot of insight, how are you actually taking it up to the next level test where you can actually make it more sophisticated? 20 years back, our rigs had 4 thermocouples measuring temperature, 3 of them measuring pattern factor, and you had 3 dots. Okay. Today we have boundary layer thermocouples that we put to measure temperature really close to the wall. Why? Because we are driven by the need for us to get really accurate temperatures at the turbine wall. We are cutting off heat, amount of air that we are going to give for cooling. Okay, and I think Mahesh asked about performance. I think more than performance, we sell engines to our customers who are airliners. They are more interested in SFC, specific fuel consumption, and they want us to bring that down by about a certain percentage. That drives us in all our design. Combustor being a component does not contribute to all of it. Performance per se, if you look at it from combustor point of view, from combustion efficiency, we don't get anything in performance. It's actually the rotating parts that give us performance benefits. The combustor, we are absolutely confident of burning fuel and air and releasing all chemical energy into heat. I don't think that is our bigger challenge. The bigger challenge is how do we operate it across various operating conditions? How do we operate it at really high altitude and at really low temperatures? At that time, combustion efficiency becomes a kind of an important parameter. But normally, the efficiency that you quote, which is basically at cruise, we are absolutely certain that we will convert every damn fuel into heat.
I have a thought in this that given that industry wants finally its codes to do all the prediction, so any of these processes, if it were possible to break it up into building blocks of rudimentary experiments. I use the word rudimentary here with caution in the sense that we've had recently a very successful collaboration between Boeing, Airbus and NAL where they wanted to look at the aeroacoustics of landing gears. And they designed, and this process design took like a year, in which they designed a landing gear which was rudimentary in the sense that it had enough complexity to capture the physics, yet it would be tractable enough that both the modeler as well as the experimenter could give meaningful data. So given that there are these three groups and academia, I know everyone would like to play in their sandbox, but if industry could sit with academia and design a rudimentary injector, say, in which, given that so much depends upon the configuration of the injector, whether it's the ligaments or droplet breakups, if it could be a mutually agreed rudimentary experiment, we could find ways of developing, if necessary, new diagnostics to deal with that. And you could, for that rudimentary case, try to fine-tune your codes. And this would, again, be just part of a multi-phase experimental goal. I mean, not one integrated that.
Only combustion efficiency we have to see in terms of length. Any gain in length, efficiency remains same. Any gain in length with the same efficiency is beneficial. It indirectly atomization supports. Another thing is the condition, you said geometrical, which condition, atmospheric. If you think geometrical variation you have to study, you have to go for higher pressure. Because if you go at low pressure, we don't know how you are captured, which is a very complex it is. What reading will get such a the flow distribution, you will not be knowing which component, which part is going to affect because of that variation. So you have to go for higher pressure. No other way.
Discussion. We have come to the end of this session. So I think you guys have been taking notes, right? Yeah. Okay. So we'll try to summarize these so that in the afternoon session, perhaps we could, revisit some of these points to come up with a more map for moving in the future. So thank you all, and we can move to a coffee break. Thanks.